Let's take a look at the first of our two fundamental laws, Coulombs Law. Coulombs Law states that the force between 2 point charges, Q1 and Q2, is, and then we have three items here, along the line joining them. And so what this means is, and we'll look at this closer in a little bit, if we have 2 point charges that are arranged like this, our forces are going to be along this line that sort of joins both of those points. So what we're saying is we're not going to have some force going in some different direction like this. The second item here is that this force between the 2 points is directly proportional to the product of the charges. So we have direct proportionality to the product of the charges, and third, it's inversely proportional to the square of the distance r between them. So we can combine these last two items pretty easily and get a rough equation. So we can say our force is equal to, we know we're going to be directly proportional to the product of the two charges, Q1 and Q2, and inversely proportional to the square of the distance between them. And we're also going to have to include a constant K, and I'm going to come back in a minute and describe what that is. And then with our first point, we're going to come back and look at sort of a really simple example so we can get a better handle on what direction this force should be in. So of course right now this is just a magnitude. But before we look at any of those items, what I want to do is come back and define more clearly what I mean when I say point charges. So I've kind of been throwing that around, but let's come back and explicitly define that. Okay, so a point charge is essentially if we just have a charge on something that is really small compared to all of the other distances and dimensions that we're dealing with. So formally we can say that a point charge is a charge located on a body, and the dimensions of that body are much smaller than any other relevant dimensions in the problem. So charge located on a body whose dimensions are much smaller than other relevant dimensions. And so for instance, a relevant dimension of course would be the distance between the two charged particles. So if our bodies where the charge is residing is really small compared to the distance between that body and another body, we can essentially assume it's a point and it doesn't take up any space. So now coming back to this constant that I just sort of randomly added in here, K, what is that? So it turns out K is something called our proportionality constant. So lowercase k is our proportionality constant. And if we're using SI units, so if we have everything in terms of coulombs, meters, newtons for our charge, distance, and force respectively, then our proportionality constant is going to be equal to 1 over 4 pi epsilon naught. And so if we plug these numbers in, we get approximately 9 times 10 to the 9th meters per farad. And so you'll notice I've sort of slipped in yet another variable here that we've not defined yet, and that's this epsilon naught. However, you might be familiar with this from previous classes, and this epsilon naught has a value of 8.854 times 10 to the minus 12th farads per meter, and this is our permittivity of free space. And so this is definitely a constant that we're going to be using a fair amount, so I would suggest you definitely have that written somewhere in your notebook or on your note sheet. I believe it's in the front cover of the textbook along with some other useful constants as well. So knowing that proportionality constant, we now have a full equation for the magnitude of our force, but now we want to come back to that first point about the force being along the line joined in them. We want to add a direction to this force equation. So in order to do that, we're going to consider a relatively simple figure. So let's say we have 2 point charges. So I'm going to draw one here and one here. So let's say this is our Q1 and this is our Q2. And we're going to define their location in space with their position vectors. So if I'm talking about position vectors, that's going to be relevant to the origin. So I'm going to draw my origin over here. And so we can say we have a position vector for Q1 that's equal to R1. So this is position vector R1. And from the origin to Q2, we have position vector r2. Okay, so now what we want to do is we want to figure out the force on Q2 due to Q1, and then we'll come back and we'll say how does that relate to the force on Q1 due to Q2. It turns out it's going to be equal and opposite, assuming that the two charges have the same charge magnitude. Okay, so what we can do is we can define a distance vector between the 2 point charges. So I can write a vector like this, and so just to match what I have in the notes, we can look at the direction vector going from 1 to 2. So remember in our notation, we have r sub 1, 2, so it's where are we starting and where we're going to. And so once we have this, we can now update our force equation to contain a direction. So what we can say is the force on Q2 due to Q1, and the notation for that is we're going to call that F12. So again, just be careful with that notation because it's the force on 1, or sorry, I got that backwards. It's the force on 2 due to 1. And so again, it's easy to get yourself tripped up as I just did there, trying to describe that, so make sure you're careful with this notation. But this force on Q2 due to Q1 can then be written as force on 2 due to 1 is equal to, so we're still going to have the product of our two charges, Q1 and Q2 in the numerator, and now writing out that K explicitly, remember as 1 over 4 pi epsilon naught, so I'm just going to put a 4 pi epsilon naught in the denominator, distance squared, and now I'm going to put a direction, U of r12. So I have a unit vector in that direction of r12 between the 2 points. And so what that's telling me is that my force vector is going to be something like this. So this would be force 1, 2. So let's box that equation in, so that's going to be a useful one. And again, we're going to come back and describe this explicitly in the next video, but what we could see is that the force on Q1 due to Q2 is going to be in the opposite direction. So we'd have it in the direction of the unit vector of r21. So this is F on 1 due to 2. Okay, and so notice that I've maybe drawn that slightly off, but this should all be in a straight line between the 2 points. And so that's our point 1 of Coulombs Law. One other thing that I want to look at is a modified form of this box equation where we can rewrite this using position vectors. So can rewrite with our position vectors. And so which equation we're going to use, the one that's boxed or the one that we're going to show here in a little bit, depends on what information we have available. And of course we can get the one sort of set of information from the other, but sometimes if we're given position vectors, then maybe it's going to be easier to plug directly into equation as opposed to having to calculate the distance between the two. So what we can say then is we're looking for sort of a relationship between this unit vector and our position vectors. So in general, our r12, so that's the vector from Q1 to Q2, is equal to, so thinking back to our algebra, our vector algebra, it's equal to r2 minus r1. And then of course the magnitude of that vector, r12, is equal to the distance between the 2 points r. And so what we can say then is that unit vector, r12, is equal to the vector r12 divided by r. So sort of putting all three of these pieces of information together, what we can say is that that F12, the force on 2 due to 1, is equal to, so we still have the product of our charges, Q1 and Q2. We divide by our 4 pi epsilon naught. But now what I'm going to do is I'm going to pull this r from our unit vector and multiply it with the r squared that was already in here. And so of course that's going to give me an r cubed. And now I just have r12 as opposed to the unit vector. And so of course I can rewrite that as well. So I can say this is Q1, Q2, and then I can expand this out and say this is r2 minus r1 divided by 4 pi epsilon naught times the magnitude of r2 minus r1 cubed. And so this is a different form that we might sometimes want to use. And again, whether you use the top form here or the bottom form ultimately depends on what type of information you have available, or rather how the information is presented. Of course, we could convert so that we could use one form or the other, but sometimes it's just more convenient to go with one. In the next video, what we're going to do is come back and talk a little bit more about some of the important properties of this law, and then we're going to talk about our electric field intensity before taking a look at some examples.